Good morning, folks. Let's get you some background on superconductivity. And this gives a really good reference source if you want it to be. But this is a superconductor technologies company, or should I say incorporated, INC. And yeah. Let's read it. What is superconductivity? Superconductivity is a phenomenon where some materials exhibit no electrical resistance below certain cryogenic temperatures. Superconducting wire. Superconducting wire is made of superconducting materials, which, when cooled below its transition temperature, has zero electrical resistance. See the image to the right. Often the superconductor is in a filament form or on a flat metal substrate encapsulated in a copper or aluminum matrix that carries the current should the superconductor quench or rise above critical temperature for any reason. High-temperature superconducting wire, HTS. There are two well-recognized types of high-temperature superconducting wire, SCCO, known as first generation 1G wire, and REBCO, known as second generation 2G wire. REBCO stands for rare earth barium copper oxide for the superconducting compound. BSCCO stands for bismuth strontium calcium copper oxygen. Each of these processes has been refined over 20 years of time, and each type of coated conductor has trade-offs. The driving element that classifies each is operating temperature. Most importantly, by significantly reducing the overall system operating temperature, HTS device manufacturers can realize power output increases in the magnitude of 10 times. First generation 1G HTS wire. First generation 1D HTS wire has been commercially available since 1990. During 1G HTS wire manufacturing, the powdered superconductive material fills silver alloy pipes. These are subsequently processed in a multi-filament HTS wire by means of a special rolling technology. The most commonly used materials in early HTS were bismuth-based, specifically bismuth strontium calcium copper oxide, BSCCO, pronounced BISCO. These materials have been used to construct a variety of HTS power devices, including transmission cable, transformers, fault current controllers, motors, and generators. And though 1G HTS wire operated at high temperatures and addressed the problem of costly cryogenics, the heavy reliance on silver as a raw material made the wire far too expensive to commercially produce. Recent improvements in 1G HTS wire performance has begun to shift this economic fault. Second generation HTS wire, 2G. A majority of superconducting wire manufacturers are migrating to new second generation 2G HTS materials, utilizing rare earth barium copper oxide, REBCO compounds. 2G HTS materials are recognized as a superior superconductor by offering better performance in a magnetic field and improved mechanical properties at lower cost. HTS wire manufactured with 2G HTS technology now surpasses 1G wire in electrical performance, but at higher cost. Few rare earth compounds are recognized as 2G HTS materials options. The industry currently uses a variety of rare earth compounds: yttrium, samarium, neodymium, gadolinium, with barium copper oxide, REBCO, as the choice materials for HTS wire and HTS devices. Extensive 2G HTS wire technology, R&D, pilot production, and manufacturing scaling efforts are underway. 2G HTS wire offers additional benefits with its unique properties: unmatched critical current capacity, increased in-field performance, significant cost advantages. 2G HTS devices are needed today to solve critical challenges in the power grid, increase power capacity, increase efficiency, reduce size, weight, and footprint, improve utilization of assets. Medium temperature superconducting wire, MTS. XGS wire types using a magnesium diboride or MGB based process are usually produced by reaction of fine magnesium and boron powders, thoroughly mixed together and heated at a temperature around or above the melting point of pure magnesium, greater than 600 degrees Celsius. MGB2 wires and tapes are therefore realized by means of the so-called powder-in-tube method, or PIT. Thanks to the higher operating temperatures, MGB2 systems can be cooled by modern cryocooling devices. The main competing advantages for MGB2-based HTS wire manufacturing are low-cost raw materials and relatively simple deposition techniques. In contrast, MGB2's low critical temperature TC of 30 Kelvin is limited to applications that operate at lower temperatures of about 20 degrees Kelvin. Low cost continues to be the main driver for MGB2 wire manufacturers. However, because of its relatively simple PIT deposition or pit deposition approach, many believe that MGB2 may be in the near term better serve applications like electronics in the form of flexible flat ribbon cables and superconducting cavities for RF applications. The MGB2 is a superconducting wire alternative operating at 20 degrees Kelvin, a temperature between LTS, or low temperature superconductors, around 4 degrees Kelvin, and HTS, 65 degrees Kelvin. Primary focus for HTS motor and generator applications. Price and performance is very attractive. Performs very well in high magnetic fields. Must operate between 15 to 30 degrees Kelvin. Poor physical properties. Cooling costs are more expensive and less reliable than liquid nitrogen. Not practical for HTS cable application to demonstrations, although demonstrations are underway. Low temperature superconducting wire, LTS. Low temperature superconducting technology operates at liquid helium temperatures, 4 Kelvin, which was discovered in 1911. This technology became commercially successful in the 1960s when the wire was made from LTS materials for use in superconducting electromagnets. LTS electromagnets create fields that are much stronger than conventional copper-based electromagnets. Notably, these state-of-the-art LTS electromagnets enabled new technologies like magnetic resonance imaging, MRI, and nuclear magnetic resonance, NMR. LTS superconducting wire is manufactured with niobium titanium, NBTI, or niobium tin, NB3SN, using a powered-in-tube process embedded in a non-superconducting matrix, such as a silver alloy, somewhat similar to the way traditional wire of copper or aluminum is made. Though LTS wire can be manufactured at costs competitive with copper, LTS materials or devices are very expensive due to the high cost of cryogenic cooling and their reliance on silver. As a result, LTS technology remains quite limited to niche and specialized applications, e.g. the Hadron Collider. In 1987, materials were discovered that exhibited superconducting properties at temperatures as high as 90 degrees Kelvin. This class of materials was called high-temperature superconductors, or HTS. While this is very cold, it was a significant breakthrough. And these materials could now be cooled by liquid nitrogen, which is a much easier thing to work with, and more readily available without supply issues, and most importantly, considerably cheaper than liquid helium. This drastic cost reduction in cryogenic systems opened new opportunities for superconducting applications. HTS communication devices, maglev transportation, superconducting power cable, and superconducting motors and generators were now economically possible. As with LTS devices, many HTS devices use superconducting wire as a base technology. Features of LTS. Here we have it. They are designed to only operate at 4 degrees Kelvin, therefore limiting to motor and generator applications. Cooling cost and reliability key robot to market entry. Liquid helium required for cooling, which is a scarce resource. LTS is in full production use in MRI devices and can be scaled to meet demand for new MRI and NMR devices. Good in-field performance and strength, anywhere from 3 to 10 Teslas. Very cost competitive, excluding the cooling costs. And there you have it, ladies and gentlemen. Different kinds of wire. So we have low superconducting wires, low temperature superconducting wires, medium temperature, and high temperature superconducting wires. And it's all from this website, Superconductor Technologies Incorporated. Alright, ladies and gentlemen, I hope you enjoyed this session. Cheerio.